You know, over the years, we've lied to you a lot in mathematics. Like in primary school, we would have been questions like this, and we'd give you a question, what's 5 minus 6? And you'd go, can't fool me. Can't take 6 away from 5. And then we do things like that, and then we introduce these ideas of negative numbers, and then all of a sudden, oh, I can take 6 from 5. And even fractions are the same, you know. What's 8 divided by 3? 3 doesn't go into 8, you can't do that. And then we introduce this idea of fractions, a new type of number, and we can do it. And it's the same with everything. You know, we come up against a problem and we say, well, hang on, we can't do that. And so we invent a new, well, we don't invent, we discover. They're always been there. So it's not like we invented them, but we discover a new set of numbers. And the set of numbers now we're going to look at are the complex numbers. The myth that's around is that the reason we have them was because of the solving quadratics. That's what brought up the problem. Well, that's not actually true. It was actually the problem of trying to solve a cubic that brought up this idea of imaginary numbers. But anyway, let's go to solving quadratics. And here's a very simple one. X squared plus 1 equals 0. And so we go, okay, well, let's move the 1 to the other side. And we go x squared equals negative 1, and that's when we've come up with this problem. Can't do it. X squared can't equal negative 1. So we said there was no solutions. Or more correctly, there were no real solutions. So we come up with a problem. We have a new class of numbers. So we define this new number. We say, well, we don't know what the square root of negative 1 is. So we're going to give it a name. And that name we give it is the pronumeral I, which stands for imaginary. A very poor choice of words, because when they started calling them imaginary, people thought they didn't exist because they're imaginary. But they do exist, just like negative numbers do exist. It was just a poor choice of naming, which made people think, oh, they don't actually exist. They do exist. It's just a different type of number. So I is equal to the square root of negative 1, or maybe more correctly, I squared is negative 1. So now we can go and solve it, because we go, okay, well, x then is plus or minus the square root of negative 1, and I know the square root of negative 1 is I, so my answer is plus or minus I. Okay, so every single complex number we can write in this form, x plus iy, where, so all complex numbers contain a real and imaginary part. In a way, it's a bit like what we just looked at with vectors. We're breaking it into components, a real component and an imaginary component. So the real part of the imaginary number would be the x, the imaginary part of the imaginary number. The imaginary part of the complex number is y. Notice y is a real number. Okay? So when we say iy, I is the imaginary part. And we're saying that's times a real number. If I have 3 plus 5i, and they said, what's the real part? Well, the real part's 3. What's the imaginary part? Well, the imaginary part's 5. It's not 5i, it's 5. Now, if the real part is equal to 0, that is an imaginary number, or sometimes called a pure imaginary number. Okay, so some examples of that. Oh, root 3i minus 6i. In fact, anything times I. Now, if the imaginary part is equal to 0, well, that's what you've been working with your whole life. That's just a real number. So some examples of real numbers. Oh, 3/4, pi, e, negative 4. Every complex number has a conjugate, a complex conjugate in this case. Now, we've seen the idea of conjugates before. And the idea of conjugates was, we saw it in surds, you might recall. So it's not a coincidence, because when you think about it, these are surds, because I is the square root of negative 1. So it's the same idea as a surd. So we have a conjugate. If z is x plus iy, the conjugate, and you'll notice the bar on top of the z there, so that's our symbol for conjugate, we put a bar on top, and that'll be x minus iy. So we change the sign of the imaginary part. So if my complex number is minus 2 minus root 7i, okay, so the conjugate would be minus 2 plus root 7i. All right, so let's look at our set of numbers. So we have the set of real numbers. That's what we've seen so far. All real numbers can be placed on the number line. If it can be placed on the number line, it's real, and our symbol is R. Now inside our real numbers, we have the rational numbers, symbolized with Q, because remember Q stands for quotient. Rational numbers are any number that can be written as a fraction, A over B, where A and B, no common factor. Anyone know a fancy word for that? Coprime. Coprime is another way you could say that. Then you have these irrational numbers. They're the ones that can't be written as the fractions. Now, we don't actually have a symbol for irrational numbers. A way we could do it to say, well, it's the real numbers, but excluding, so the backslash is excluding the rational numbers. Then, inside the rational numbers, we have fractions. Now, by fractions, I mean the ones that aren't whole numbers. So then we do have the whole numbers. We have a fancier word for that, integers. And remember, the symbol for integer is Z, because Zahlen is German for integer. Now, inside the integers, we have the natural numbers. And the natural numbers are, positive integers, sometimes called the counting numbers, and N's the symbol for that. Then, of course, inside, we have this other weird number, which does all sorts of strange things, but 0. And so 0 sits inside the integers as well. Overriding all of those, we have negative numbers. You can have negative fractions, you can have negative integers. Notice it doesn't overlap the naturals, because you can't have negative natural numbers. And it doesn't overlap 0, because, well, negative 0 doesn't make sense. But you can have negative irrational numbers. Okay, so that's our set of numbers that we know so far. So now, we can actually surround all that and say, well, we now have the set of complex numbers. So real numbers are complex numbers. They're just the ones where the imaginary part is equal to 0. Complex numbers, C is the symbol we use for complex numbers. Okay, so real numbers when y equals 0. Then over here on the left, we now have our imaginary numbers. And that's when x equals 0. So our imaginary or pure imaginary numbers are when x equals 0. They can't be ordered. That's the weird thing about imaginary numbers. So you can't place them on the number line. So if you can't place them on the number line, how do you say this one's bigger than this one? It doesn't make sense when you start talking about the imaginary numbers. How do we then go and work with them? So as I mentioned before, they're basically surd. So all our surd operations work with complex numbers. So if I want to add, same as we would with surds, we say the irrational part would add with the irrational part and the rational with the rational. The two don't meet. Well, it's the same when we're talking about real numbers and imaginary numbers. Remember that set of real numbers? There was no point of intersection of the two. So you can't mix them. So you just add the real part with the real part and the imaginary part with the imaginary part, and we get -4 minus I. It's obviously the same with subtraction. When you think about it or look at it, it's pretty much just like doing algebra. 12 minus 5i. Multiplication, again, just like algebra. We use our first outside, inside last, like our binomial product. But the difference is, once I see I squared, well, I know I squared is equal to -1. So that 6i squared is actually a real number. It's -6. The reality is I probably wouldn't write that second line down. When I'm expanding it out, I would be in my head going, oh, well, -3i times 2i, that's actually going to be +6. Because it's -6. And then, tidying it up, -26 plus 32i. So division, and division is what we call realizing the denominator. So in surds we call it rationalizing the denominator, because the idea is we wanted a rational number on the bottom. Well, with these, we want a real number in the denominator. So we're realizing the denominator. But the idea is exactly the same. How did we rationalize the denominator? We multiplied by the conjugate. So we do the same here. So -8 minus 2i. So on the bottom, beautiful thing about conjugates is we're always going to have the difference of two squares, but now it's not going to be the difference of two squares. It's going to be the sum of two squares. So on the bottom, instead of getting 64 minus 4, we get 64 plus 4. And that's because of the I squared being -1. Top tidies up. You could, I suppose, leave it as the second last line, but we tend to split it because, again, we say, oh, this is the real part, this is the imaginary part. Okay, some basics about conjugates then. When you're finding conjugates, you could find the conjugate first of each number and then add them, or you could add them together first, then do the conjugate. You should get the same answer. Same with multiplication. You could do the conjugates first, then multiply them, or multiply them first, then the conjugate. And division, it's the same as well. Z conjugate will give you, that's the one I was just talking about, sum of two squares. So you always remember that. If you see a number times its conjugate, sum of two squares, real part squared plus imaginary part squared. And if you want to find the reciprocal of a complex number, it will turn out to be the conjugate over Z conjugate. Because when you think about it, all I've done is multiply top and bottom by the conjugate. But on the bottom, Z conjugate is the sum of two squares. So if I want to find the reciprocal of 4 minus 3i, well, on the top is 4 plus 3i. On the bottom, sum of two squares. 16 plus 9 is 25. So we get our answer. All right. Now, equations involving complex numbers. If two complex numbers are equal, the real part equals the real part, the imaginary part equals the imaginary part. It goes back to what I was saying. There is no point of intersection of the two sets. So formally, if A1 plus B1i is equal to A2 plus B2i, then the only possibility is that A1 equals A2 and B1 equals B2. All right, I've got this one to solve. Well, there's a couple of ways I could approach it. I could divide both sides by 2 plus 3i, or I could expand out the left-hand side. Which way did I do it? I've expanded out the left-hand side. Okay, so expand out the left-hand side. Notice minus 3y. See, I didn't write the I squared down. I automatically just went, oh, well, I squared's -1, so I get minus 3y there. But the real part must equal the real part, so 2x minus 3y must equal 4, and the imaginary part must equal the imaginary part, so 3x plus 2y is -2. Couple of simultaneous equations. Let's solve those. X is 2/13. Sub back in, and we get the y is 16 on 13. Notice that is the answer. The answer is not 2/13 plus 16 on 13i. Because the equation is saying find x and y. It's not saying find what x plus iy is. You could have simultaneous equations involving complex numbers. So w and z are both complex numbers. But the rules don't change. You just want to eliminate. So we'll make the coefficient of either the z or the w the same. I've made the coefficient of w the same. So I've multiplied the bottom one by 2. So 3z is 2 plus 5a. So I know what z is. Go and substitute back in. So exactly the same rules. They aren't changing. And then now let's play around with that to work out what w is. We've got 2iw is 10/3 plus 4/3 I. Almost there. We don't leave it with the imaginary part on the bottom. We always realise the denominator. That's because of comparison. Because if I'm going to say imaginary part equals an imaginary part or something like that, I need to have it times I. I can't have it divided by I. So when I realise the denominator on that one, we get minus 5/3 I. So there's our 2 points. Okay.